So in this video we are going to look at some examples of the one sample t interval for mu. So remember what's going on here. We've got a sample. We don't know what sigma is, so we use S, and that tells us we have to use a t critical value off of our t table, and so this is going to be the formula that we're going to use to get a confidence interval from mu. All right, so first example. A sample of size 19 is taken from a normal population. The standard deviation is found to be 1.6 and the mean is found to be 11.7. So let's stop right here and write down what we're given. A sample of size 19 is taken. So what does that mean the 19 is?
N.
That is N. That's usually the easiest to get.
So would it be 18 then?
No. N is still 19. That's the degrees of freedom and the sample size are two different things.
Okay.
Yeah. So N is still 19. But your degrees of freedom would be 18. The standard deviation is found to be 1.6. So we take a sample and then we find the standard deviation is 1.6. So that means the 1.6 is S. It's a statistic. It's a sample standard deviation. So S is 1.6. And what about this 11.7? That's X bar. Anybody have any questions on that? Okay. So what's the point estimate for mu? What's our single number that's our single best guess for what we think mu is? Probably not right, but 11.7. All right. Number 2, create a 90% confidence interval for mu. All right, so let's do that. So, since we just went over this T procedure, that's probably what we're going to use, right? Why do we know, or how would you know if you were just to do this on an exam or something like that? How would you know that you're using the T procedure here? We don't know sigma. We don't know sigma. We know S, we don't know sigma. So the formula that we're going to be using here is X bar plus or minus a T critical value, and the T critical value is going to have degrees of freedom of n minus 1. Times S over the square root of n. So X bar is 11.7. The T critical value, we'll look that up here in a moment. I'll get the T table out and put it here. S is 1.6. And we're going to divide by the square root of n. Not n minus 1, it's the square root of n. It's the square root of 19. The n minus 1 only comes in when we're talking about the degrees of freedom. Okay, so let me grab that T table, and this is posted in Moodle, and you can find these probably online or wherever you want. So the way this works is this table is completely and entirely designed to give you guys critical values, T and Z critical values for confidence intervals. That's why this thing exists. So 99%, 98, 95, 90, and 80, this is the confidence level, right? The columns are the confidence levels. And all you have to do is pick the correct degrees of freedom. And as I mentioned before, if you want to do a Z interval, remember I said, oh, those Z critical values are going to be located somewhere. Where they're located is in this table. You say, well, this is a T table. It is, but remember, a T with infinite degrees of freedom actually is the Z. So the bottom row of your T table is actually Z critical values. And we've seen some of these before. Like right here is 1.96, right? We've seen that one before. And here 1.6449, well that's basically 1.645 and 2.576 and stuff like that. So the bottom row is for Z. So you can, that's where those are located. You've got those now. All right, so how many degrees of freedom are we going to be using for our interval?
18.
Right, so N was 19, so we're going to be using 18 degrees of freedom. So I go to the row that says 18, which is n minus 1, one fewer than the sample size.
And then to 90.
And then what confidence level did I choose?
90%.
Is it 90? Okay. So 90% is the fourth column, right? So 1.7341, if I'm looking at that right.
1.7.
Is that what I said? Yeah, 1.7341. So does everybody understand how to use this now? It's pretty easy. It's I think pretty helpful. 1.7341.
And that would be time S over.
Square root of that. Okay, so at this point we can find the margin of error. You still have a margin of error on these things, and that this piece right here is still the standard error and stuff like that. So a lot of the terminology is still the same. So the margin of error, if I'm calculating this correctly, is 0.6365. And then we can actually calculate the interval, do 11.7 minus the margin of error, and then 11.7 plus the margin of error. It should give us what we want. So I'm getting 11.0635. Is everybody okay with that? So this is our 90% confidence interval for mu. So we're 90% confident that mu is contained.
I think mine's rounding up, so yours 0.0635, mine's going 11.064 is what it's.
I'll take a look at what yours is after I finish the examples, Jared. Let me do this, and then I'll come by and look at your calculator. Any questions on this? Okay, so that's number 2. That's our 90% confidence interval. Number 3, show that you check the proper assumptions. There's 3 of them. X bar normal. We have to have a simple random sample. And for this one, sigma unknown, right? Because we did the T procedure. X bar normal.
Yes.
Yes, why?
You said population.
I didn't say X bar was normal.
You said no population.
I said the population is normal. The population is normal implies X bar is normal, but I didn't tell you X bar was normal. So X bar is normal because the population is normal. Simple random sample. I intended to put that there, so yes. So I intended to give that to you. And sigma unknown, sure. It's really easy to assume you don't know something, right? There's a lot of things I don't know. It's easy to assume. Yeah. So that's number 3, we're good in terms of assumptions. Number 4, is it reasonable to think that mu is 11? Remember, the way to think about this is draw your number line,
Yes.
draw your confidence interval.
Yes.
Our confidence interval goes from 11.0635 to 12.3365. Here's 11. Remember, for it to be reasonable to think that mu is 11, 11 would have to show up in this interval. Remember, this 11 is called our mu claim. It's a claim value for mu. So since 11 is outside of our interval, is it reasonable? No, it's not. According to our interval and our calculations, it's not reasonable to think that mu is equal to 11. So if not, how different do we think it is? We subtract it. This distance right here is called what? MVD, minimum verifiable difference. And the MVD is just this distance, so which is 0.0635. Okay? So we're okay with that? Okay. Next example. Any questions on the last one before we move on? On this one, it says a simple random sample, so I actually said simple random sample here. A simple random sample of college students was taken, their ages were recorded, and are given below. So we want to know the point estimate, and get a confidence interval, and all that good stuff. I didn't give you n, did I? I didn't say what n was. I didn't say how big the sample was. Did I tell you what x bar was? Did I tell you what s was? But wait, I actually gave you the data. If you actually have the data, can't you calculate all those things? Yeah, you sure can. So, I'm typing these into computer, and I'm going to get the summary stats for them. There's a bunch of different ways you could do this. You could use your TI, you could use Stata, you could use SPSS. I'm going to use R here real quickly since I've got it open. 18, 19, 19, 25, 20, 36, 30, and 24. Okay, so using the computer, I found that x bar, the average of those, is 23.875. If you're having trouble getting those, I can help you. The standard deviation of those values is 6.3569. And there's 1, 2, 3, 4, 5, 6, 7, 8 of them, so n is equal to 8, isn't it?
So how'd you get the S?
I used the computer here. If you use your, I can show you how to do it in Stata. I can show people how to do it in SPSS. You can use your TI to get all these at once. So right now, let's just do it this way, and then we can maybe do another one where we talk about how to actually get those values. I'll show you a bunch of different ways to do it. Yeah. So what's the point estimate from you? That's just x bar, which is 23.875. Get a 95% confidence interval from you. Okay? Well, how do we know that we should use the T procedure here? You can't get sigma unless somebody tells you magically or something like that, right? If you just have a sample, you don't know what sigma is. So we're going to do a 95% procedure. So that's going to be x bar plus or minus a T critical value, because we're doing the T procedure, we don't know sigma, times S over root n. X bar is 23.875 plus or minus the T critical value. Let's look at our table. How many degrees of freedom should we be using here? 7 degrees of freedom, 95%. Was it 95? Yeah. So 7 with 95 is 2.3646. S is 6.3569. Divided by the square root of n, we said n was 8. There's 8 observations. So the margin of error I'm getting is 5.3144. So we'll take x bar plus or minus that. And so our confidence interval if I'm doing my calculations correctly here, 18.5606. up to 29.1894. So that's our 95% confidence interval from you. All right, in terms of assumptions, X bar normal. Did I tell you the population was normal? Do we have a really big sample size? We don't have either one of those, do we? Let's put a question mark right now. When you have a small sample size, you have to somehow know or assume that it's reasonable to think your population's normal. So maybe there's some things we could do to explore that a little bit. But let's not do them right now. We'll do those here in a moment. Simple random sample, that was given, right? Sigma unknown, sure, it's easy to assume you don't know something. So the one thing we're going to need to check here, the thing we're going to need to explore, is it reasonable to think that our population is normal? Let's ignore that right now. We'll go over that in part 5. But in part 4, is it reasonable to think that mu is 18 according to our interval, assuming that we're valid in creating this interval?
No.
The answer is no. Here's our mu claim, and our interval goes from 18.5606 up to 29.1894. So the answer is no, it's not reasonable to think that mu is 18, and this little distance right there is called what? MVD, and our MVD in this case is 0.5606. So our MVD is 0.5606. Okay, let's think about number 5. I know I'm kind of rushing through this because I wanted to actually get to number 5 here. Number 5 says, is the normality assumption realistic? We can't rely on the central limit theorem. We don't have a big sample. But what we could do is say, okay, well, we think the population's normal. So we have a sample, and we need to know, is it realistic to think the population from which that sample was taken is normal? Didn't we do that sometime before? Think about Unit 1, right? We did assessing normality. Remember we used SPSS and a bunch of stuff? That's why we did it, because there's going to be cases like this where you have to do that. Remember, we did 3 things. We did a normality test, we did a histogram, and we did a QQ plot. Which one of those was best for small samples? QQ plot. That's the one that's going to be most valuable, because that's going to be the time that we're doing this. So what I'm going to do here real quickly is I'm going to put together a QQ plot. So we can use, we can do this in any number of ways. Switch it over. This is a QQ plot of these data, of these 8 points. What is it that we're looking for in the QQ plot that would indicate normality? Now we can't prove normality. Linearity indicates normality. So if these points are basically linear, now that's not going to be 100% the case. You know, basically we do not want to see some pattern of curvature. Do we think we see a pattern of curvature here?
Yes.
Kind of, yeah, because if you look at it, it looks like there's something like this. So in number 5, that's what I'm asking you to comment on. And a QQ plot's fine. You don't have to do any of the rest of it. So number 5 says, is the normality assumption realistic? Probably not.
Looking at the QQ plot.
And that's because the QQ plot has systematic curvature. So what we don't want to see in the QQ plot is systematic curvature. Now, because of this, should we not use the t interval? Maybe not. Maybe we're not comfortable assuming that x bar is normal, in which case we shouldn't use the t interval. Do we just throw up our hands in the air and say we can't do anything? Well, there's other procedures. No, the z wouldn't be any good either because we don't know sigma. There's other procedures out there that people have developed. Now, in this class, we really don't have time to go through all of them, but there are other things we could maybe look at doing.